In this lecture, we are going to discuss the multiple reaction concept. Multiple reaction means a reaction which involves with two stoichiometries, more than two stoichiometries. Like here, as you can see that we have a reactant, it is getting decomposed to form two products called as R and S. Out of these two, the R is considered as a desired component, like the product what we require. Whereas the S is called as the unwanted product, it forms because of the supplementary reaction or side reactions. So now we would like to see the condition, because we know that since we are getting a multiple product here, we would like to focus only on one compound. R is my desired compound, S is the unwanted product, as you can see from the name itself. Now I want to maximize the amount of R in the final mixture. Okay, your reaction mixture will be having three components, like product R, product S, and unreacted A also will be present. Now my objective is to maximize the amount of R in the final mixture. For that, what is the condition to be followed? So what is the type of reactor we have to use? That we are going to understand here from this discussion. Actually, what we can do is that for the first step of reaction, like this reaction stoichiometry, we can write the rate equation as like this. So rate of formation of R is equal to K1Ca to the power of that A1 is written. A1 is the desired reaction order, that A1. Okay, like the A2 is nothing but undesired reaction order. So like that I have written. So next step what you can do is that divide the rate equation. In the previous slide we have seen the rate equation for both the stoichiometries. See, now on dividing the rate equation, we can see that this time factor will be getting cancelled. See, if you divide this by this, what will happen? RR by RS. So this dt will be getting cancelled. Okay. So the Ca will be having the Ca term is common in the ratio. That means we can add the power like what it is shown here. So the time variable will disappear there from the equation, final equation. Now this ratio is very crucial, very critical, because it is a ratio between moles of R formed by moles of S formed. Now our aim is to find the find the condition that maximizes the amount of R formed. So this ratio I need to get more. Okay, because if it is high means then moles of R formed is high, moles of S formed is less. So the condition now I would like to get. For that this ratio depends on only this concentration value as well as the reaction order. These two parameters decides the ratio value. Okay, so now for example, if the ratio, like the reaction order is there, right? You can see here that the reactant concentration is the only factor. So this ratio it depends on the concentration, reactant concentration. So that determines the value of this ratio. This ratio should be high. If it is high means the numerator portion is high. Okay, that condition only I want to get. So for that, what are the conclusions we can give here is that now in this equation, like as we know that we have to adjust the value of the concentration. Okay, so for that three conditions we have to observe. Say for example, if A1 greater than A2, as I told you, A1 is the desired reaction order. So if it is more than A2 means then what will happen is that if we go back to previous slide, this become positive, this become negative, larger value, this is larger value. Okay, so your Ca power is a positive value now. Ca power, you are getting some positive value. That means the ratio proportional to concentration. Ratio proportional to concentration. That means if the concentration of reactant is at the highest level, then the ratio also will be somewhat a high value. Okay, so for that type of like reactor we have to use for the process. Suppose if A1 is greater than A2 means then the concentration, the ratio depends on the concentration, directly proportional to concentration. That means the concentration value, if it is higher, then the ratio also becomes large. Okay, accordingly we have to choose the reactor. Say for example, if I use a plug flow reactor means in plug flow reactor the concentration of the A will be at the highest level. It will be decreasing gradually only. That means the ratio also will be a better value. So like that I have to choose. Suppose if the A1 value is less than A2, okay, as I told you now, if A1 greater than A2, a batch reactor or plug flow reactor would favor formation of product R, because in both the reactors the concentration of reactant A will be maintained at the highest level. Okay, that will facilitate the formation of more amount of R. Suppose if A1 is less than A2, like the desired reaction order is less than the undesired reaction. So in that case, the Ca power negative value we get. So in that case, what will happen is that the ratio becomes inversely proportional to the concentration of reactant. That means lesser the value of concentration, more will be the ratio value. So in that case, we have to go for the mixed flow reactor, because in case of mixed flow reactor, the concentration of A decreases immediately as soon as it enters the reactor. Suppose if you have other case like A1 is equal to A2, like both the reactions are having same order. See, in that case, the reactant concentration will not have any impact on the ratio. We can go for any reactor, like we can go for mixed flow reactor, or we can go for the plug flow reactor. Any type of reactor we can follow for that last condition. Now, based on this, the conditions whatever we have seen, so we have a schematic diagram that explains the contacting pattern, what we can able to create between the two reactants. See, the previous case we saw the single reactant, but let us to have a case where we have two reactants called as A and B. It is giving me two products called as R and S. So A and B is the reactant, R and S is the product. Out of the two, R is the desired compound, S is the undesired compound. Okay. Now the ratio depends on concentration value, CaCb value, that we have seen in the previous equation itself. So suppose if we want to maintain both concentration of A, concentration of B high, means what we are supposed to do is we have to add A and B. So this is the reactant A, this is reactant B. This is the reactor, actual reactor. So you have to pour A and B into the reactor at a time. Okay, within a fraction of a second you have to add. If you do that, means then we can maintain the CaCb value at the highest level. Okay, CaCb low if I want to maintain, because my objective is I want to get more R. Okay, more ratio value I want to get. So for this situation, I have to add A and B like a drop by drop manner, very slowly I have to add. Then if you want to maintain like one value high, one value low, means accordingly you have to choose. So here Ca, if you want to maintain high, means then inside the reactor it is pre-filled with the reactant A. Like initially itself you have to take the reactant A inside the reactor, then Cb I would like to maintain low value. That means the B has to be added to the reactor like a drop by drop manner in a very slowly. Okay, so this is how we have to operate the system. Like if you have multiple reaction, means then our aim is to maximize the desired compound. So for achieving desired compound highest concentration, means we have to follow all these guidelines, all these rules and regulations and all. Then only we can able to maximize the desired product value. Otherwise the undesired reaction will take place, then that will spoil the entire process yield. Okay, our efficiency, everything will be getting affected. So we have to be very careful while operating the multiple reaction system. That is very important. Thanks for listening to the lecture.